Okay, in this lecture we're going to discuss transformers. Okay, transformers, we know the use of transformers. Okay, we use transformers to convert voltage. Okay, sometimes, for example, if you go to China, the voltage in China is 220. It's different than the voltage in the US. Okay, if you have anything only works with 120 volts in this country, you have to bring or buy a voltage converter. Okay, if you decide to go to China. Okay, so we do need to change the voltage in real life. Okay, that's why we make transformers, and we're going to see that's one of the reasons we use AC electricity in real life, even though it's more complicated than DC circuit. Right? When I was your age, I learned AC. This bothered me. Like, why do we decide to use AC electricity in real life? That just makes a lot of life harder, right? Why don't we just use DC, right? One of the reasons that by using AC, you can change the voltage very easily using a transformer, and it actually doesn't work in DC. So there are benefits, a lot of benefits, using AC electricity instead of DC. Okay, that's why we decided to use AC electricity in real life. Okay, so a transformer, as I said, the purpose of a transformer is to change the voltage. How does it work? How does it work? Okay, so there is a very simplified model of a transformer on the first slide. So a transformer, it's pretty much an iron core, and then has wires wrapped on this side, and then also a wire wrapped on the other side. So we call this side, say, primary, and that side secondary. So we can use this transformer to change the voltage received on this side, okay, to a different voltage on the other side. Okay, so that's the idea. All right. So how does it work? How does it change the voltage from this side to that side? You see, this side is not even connected directly to the primary side. Okay, there are two different coils. Okay, they're disconnected. Okay, they're not connected to them. They're wrapped on the same iron core, but they're not really in contact. Okay, the idea is this. Take a look at the second slide. Okay, we use E&M induction. Okay, E&M induction. Okay, so if this is connected to an AC source, that's the reason we use AC. If it's connected to an AC voltage source, right? Of course, there's going to be current here. Right, but the current is also going to be AC, so the current is changing all the time, right? But first, if there's a current and this core and this, so this is pretty much like a solenoid, right? There must be a magnetic field, right, created by this solenoid, right? For any circular current or for any current, there's a magnetic field, right? And then if you draw the magnetic field, it's going to be pretty much like this. So some of the magnetic field lines, they're going to go through that coil. They're going to go through each loop on the secondary, right? Say if this is a magnetic field. Now, so that's one of the theories we learned, right? Current is actually the real source of magnetic field. Okay. If there's a current in a loop or in a straight wire, there's always a magnetic field around it, right? It creates produces magnetic field around it. Now this magnetic field is going to go through these all these loops, right? These are also like small loops on the right hand side. So these small loops, they feel magnetic field. So they will. So for each loop, there must be a magnetic flux, right? If there's a magnetic flux through them, and if the magnetic flux is changing, there must be an induced EMF, induced voltage here, right? We learned that the induced EMF equals this. Changing flux divided by changing time. That's Faraday's law, right? If the flux through this magnetic, through each loop is changing, then there must be a voltage induced in each loop, right? So that's why there must be a EMF, the voltage induced on the secondary, right? So they're not in contact. The voltage you get on the right hand side, the secondary side, it's an induced voltage, induced current, okay? But you need to make sure the flux changes, right? If there's a flux through them, we have seen that, right? If you place like a magnet inside this like loops, nothing, you don't see any current. You have to change the flux constantly, right? So that there will be an induced voltage on the right hand side. So how do you change the flux constantly? Where does this flux come from? It comes from this magnetic field. And where does this magnetic field come from? This magnetic field comes from this current. So if I want to change the flux, I just need to change this magnetic field. So I just need to change the electric current through this primary. So I just need to connect it to a changing voltage source, right? So that's why you need to connect the primary to an AC voltage source so that you will have an induced voltage on the secondary, right? If this is not changing, there will be flux through the secondary coil, but it's not going to induce any voltage on the secondary because the flux is not changing, okay? So that's the idea. You connect this to a changing AC voltage source. So the voltage is changing all the time, right? Both magnitude and direction, both magnitude. So you will have, so if I call this V1, the I1 through this coil, the primary, is going to change magnitude and direction. So it's a sine function. We just learned that, right? It's going to be a sine function. So that means the magnetic field through this guy, if I call this V1, created by the first one, but it's going to go through the secondary, right? So this magnetic field, let's call it B1. So the change in I1 is going to have its own change in B1, right? So that's the external magnetic field to the secondary, right? So there's a change in magnetic field through the secondary. So the flux through the secondary core, it's always going to be changing. So you have a changing flux. There must be a there must be a voltage on the right hand side. So you will get a voltage on the right hand side. Okay? So that's the idea. Okay? So it's still magnetic. It's still EMF induction, even though they're not in contact. And we use this iron core to guide these magnetic field lines. So most of the magnetic field lines are going to go through this secondary core. There's still some magnetic field lines outside, but most of them is going to be inside this core. Okay, so that's the reason we wrap them on the iron core to make the magnetic field through this secondary core very, very strong. Okay, very, very strong. That's the reason. So even though this mechanism is a little bit complicated to you, okay, this is changing, so this is changing, so this is changing, everything is changing, I get an induced EMF. But actually, if you use the theory we have learned, and then you can actually find a very nice equation to predict the voltage you get on the right hand side, on the secondary. Okay, so we're not going to go through the derivation, we're just going to go ahead and use the conclusion. And it's a very, very nice conclusion. If you assume the transformer is ideal, there's no energy loss, okay, the ratio between these two voltages is always going to be equal to the ratio between these two numbers of turns, literally the numbers of turns. Okay, you just need to count how many turns are there. Okay, the ratio between these two voltages is always going to be equal to the ratio between these two numbers of turns. Okay, so it's very nice, right? So again, this can be derived. We're not going to derive it here. So don't feel like okay, we just made up this equation. This can be derived, but we just don't want to go through the derivation. We're just going to go ahead, use this conclusion. That's what we want to learn in this class. Okay. So that means, okay, so that's very nice. So if I want to change the voltage from V1 to some voltage I want, all I need to do is just control the number of turns, right? Okay. If I want to double the voltage, right, I get like 10 volts here, but I want to use 20 volts for some purpose. I just need to find a transformer which has twice the number of turns on this side than this side. Then it's going to do the job for me, okay? Or if I want to, so that's called step-up transformer, okay? If this side has more turns than that side, you connect this side to a voltage, you always get the larger one on the right-hand side. So that's called a step-up transformer. And then if you have this number of turns less than that one, it's called step-down transformer, right? Because it's just going to bring the voltage down. Okay? So if you have derived this conclusion, so it's actually very, very easy to use. Okay? All right, so now let's take a look at an example. Okay? So this is a real-life example. If you have an iPhone, the iPhone charger, or any like charger, the charger for a smartphone, okay, you see this little box, right? Okay, so what is this little box doing here? The little box is actually a transformer. Okay, it's actually a transformer. So if you read the ratings on this charger, wow, it's so hard to read. Like, do they not want people to read? So, but anyway, you can find it has the input voltage and output voltage, okay? So the input voltage is actually from 100 volts to 240 volts, okay? So it can take a voltage from 100 to 240. So that means, okay, this is good. You can use it in the US, you can also use it in China, okay? But the output is 5 volts. So what does that mean? That means if you connect this to your iPhone, okay, the voltage that goes to your iPhone is 5 volts, okay? So that is why you need to use this charger, this transformer here, because 120 volts or 220 volts in China, that voltage is too large, it's too high for an iPhone, okay? If you connect your iPhone directly to this wall outlet, that's going to damage your iPhone, okay? So what this guy does is that it's going to convert the voltage from the wall outlet to 5 volts, which the iPhone likes. Okay, so that's a transformer. You see that physics is everywhere. It's just because people don't notice that. Okay, so now let's take a look at this question. So say if an iPhone charger can convert the 120 volt voltage from a wall outlet to 5, okay, and then I want you to predict the number of turns in the secondary output winding, okay. So you're just going to go ahead and use this equation, right? So, but the biggest thing for this equation is that you need to identify which is which. You're going to have like many numbers, right? You need to identify which one is V2, which one is V1, which one is N1 and N2, right? So in this case, so say this is the charger, okay? This is the transformer inside the charger, okay? You connect it to the wall outlet. This is the wall outlet. You want to get a voltage, so you're going to connect to your iPhone here, okay? The voltage you want to get on this side is going to be 5 volts, right? You want 5 volts to go to your iPhone, okay? And then we know that the primary winding has 92 turns. Which one is primary? This is primary, right? So we want to predict how many turns are on this side, okay? So now you know which one is which, so you can plug numbers in. We're trying to find N2, not N1, okay? So you can pause the video and then finish the algebra, okay? So let's see. So the problem actually tells you the V1 is 120 volts, right? And the N1 is 92 turns. And V2 I want to get is 5 volts, okay? I want to find N2. You just rearrange this equation, you will find N2. It's going to be 4, right? So it needs 4 turns on this side to convert 120 to 5, okay? Now the next question, okay, so this is something I want you to think about, okay? But if you notice what I said at the beginning, you already know the answer and you know the reason. If the primary of a transformer is connected to a battery, so say I have a transformer, okay? And I connect it to a battery instead of the wall outlet, because the wall outlet, they're all AC circuits. If I connect this to a battery, okay, can the voltage still be changed? Say I connect this to a battery with like 3 volts. And then I have the ratio between N2 and N1 like 2. So N2 say is like 100, and then N1 is 50. Can I change the voltage to the right hand side to be 6 volts? Can you get 6 volts on the right hand side? Right? Because we know that we said that the voltage can be converted to the secondary, right? It just depends on the ratio of these two numbers of turns, right? So, but now if I connect the primary to a battery, can it do the job for us? What is your answer? The answer is no, right? Why? Remember how this guy works. You need to have changing current so that there's a change in magnetic field. So the flux through all these loops is changing so that there will be induced EMF, induced voltage on the right hand side, right? From Faraday's law for each loop, right? Of course, at the end you're gonna have a number of turns here. If you connect the left hand side, the primary, to a battery, the I1 is going to be constant. B1 is going to be a constant. There will still be flux through the secondary, but the flux is not changing. So it's pretty much like the experiment did, right? I have a solenoid. I just place a magnet inside the solenoid. I'm not doing anything. You're not going to get any current from this solenoid. You're not going to get any induced EMF, voltage, current on this side because the flux is not changing, right? So that's the reason we use AC in real life. If you use AC, you can convert the voltage very easily using a transformer. And to predict the voltage you get from a transformer, it's very easy. You just literally use the 2 numbers of turns. You can find the voltage, okay? All right, so and then you can find the voltage, the relation between these 2 voltages using the numbers of turns. You can also find the relation between these 2 currents, right? Remember, there's a current I1, there's also going to be a current I2 on this side, right? And that relation is actually very easy to figure out because if this is an ideal transformer, so the energy is conserved, right? If there's no energy loss, okay, in real life there will be some energy loss. But let's say if it's an ideal transformer, nothing is going to lose. So the energy on each side is going to be the same. So that means the power on each side must be the same, right? Because power is just energy divided by time, right? But the time is the same on both sides. Okay, so if the power on each side must be the same, you can find the relation between these 2 currents because the power equals I times V, I times V, right? So the ratio between these 2 currents, right, if you rearrange this, it's going to be V1 over V2, right? Of course, multiply, you get that. So that's actually going to be N1 over N2, okay? So it's going to be inverse of this ratio. But again, this is not a new equation you need to memorize, right? If you understand why they are true, this is true, because the power is the same, right? So you can always relate these 2 currents, right? This equation will be given. We didn't even derive this, right? This is going to be given, okay? And I believe this is easy to even remember, right? So all you need to remember is that the ratio between these 2 voltages is the ratio between these 2 numbers, okay? So by using this, you can also predict the current on either side, right? Now again, let's take a look at an example. So still this iPhone charger, okay? The iPhone charger convert 120 volt voltage from a wall outlet to 5 volts. So that's what we just did, right? The rated output current, okay, again, you can read it here, but you know, it's really hard to read. The rated output current of the charger is 1 amp. Okay, what is the input current in the charger? Okay, again, how do I find the current? I have current on one side, how do I find the current on the other side? Okay, all you need to remember is that the power is the same on either side, okay? So you always have P1 equals P2. Then you can manipulate that, okay? So you don't even need to remember there's a conclusion about the current, right? All I need to know is that, remember, okay, power is always the same, all right? But again, you need to figure out which number is on which side. That's usually a mistake people make, okay? So what the problem says is this, right? So this is the voltage. The voltage on this side, okay, is the wall outlet. So it's 120 volts. And then the voltage that goes to your iPhone is 5 volts, okay? The rated output current of the charge is 1 amp. The 1 amp is on which side? It's on this side, right? The output current. The output, this is the charger. The output goes to your iPhone, right? So that's the input. So you're actually finding the current on this side. So how do you find that? Well, just equal the power, 2 powers. You can find the current, okay? So you can pause the video and do that. But you see that if I have this, I have I1, V1 equals I2, V2, right? And the problem tells me this, and also the output current I2 is 1 amp. So you're actually finding I1, okay, not I2, okay? Don't get them mixed up. So if you rearrange this equation, you have all the numbers you need. I1, it's going to be 0.04 amp. So that's the current it draws from the outlet, okay? It's going to convert both. You see that it's going to convert the voltage. At the same time, the current is also going to change. And it has to, because power energy is conserved, right? So you don't need to do anything. Once the voltage has been changed, the current also going to become a new value on the secondary, okay? Because the power is always the same. Energy is conserved. All right, so next thing we want to discuss is the power distribution, okay? So if you know that these transmission lines, they're actually they are all at very high voltage. You should see like these signs, right? You should keep away from these transmission lines, okay? Because they are very high voltage, like thousands or even tens of thousands volts, or even higher than that, okay? So of course that's dangerous, right? You know, it may kill people, right? Okay? So, but why do we still transport this electric energy at such a high dangerous voltage? Okay? Again, there's always a reason we do that, okay? Okay? The reason is this: it's going to save a lot of money, save a lot of energy, okay? So that's what we're going to discuss now, okay? How does it save energy and money? Okay, by raising the temperature, raising the voltage on these transmission lines to such a high value, okay? So remember, we discussed that if you have a circuit, if you set a connected circuit, okay, in lab, like this, and then say this guy is like 5 volts, and I want to find the current and then power or anything on this guy. Well, you would just assume that this guy is just going to get 5 volts. Say this guy is like 2 ohms. So the current is just going to be 5 volts divided by 2 ohms. You're just going to assume this guy gets all the voltage. Why? Because the conducting wire, like the resistance, is really small, right? So they're totally negligible. You don't need to consider them. They do have resistance. They do take some voltage from this battery, but that's going to be too small. You don't really need to worry about it, okay? But transmission lines are different, okay? Because the transmission lines deliver the power from the power station to a city, say, if the distance is a few hundred miles, you're going to have transmission lines of a few hundred miles. You can't just ignore the resistance of these transmission lines, right? Because it's not like this, okay? This is like the copper wire, like, you know, very short copper wire. You can't calculate the resistance. It's going to be too small. You have some conducting wire, transmission lines, a few hundred miles. You cannot ignore the resistance, right? If they have resistance, they can take some power. They can take some energy. And this energy is just going to become heat on these transmission lines. Right? So it's totally wasted. It has been totally wasted. It's not delivered to any city, to anyone's house, okay? And you don't want that to happen. You want to reduce this waste, this energy wasted on these transmission lines. So you have to figure out some way to do that, right? So now let's take a look at it. What is the best way to reduce the energy loss on transmission lines? Okay? And it turns out the solution is transformers. Not the transformers in the movie, okay? The transformers that converts energy and converts voltage and save energy for us, okay? Say this is a power station, okay? And the power station delivers power to a city. Okay, really far away, like a few hundred miles away, right? Or even 1,000 miles away. Now, the transmission lines, they will have their own resistance, right? So if there's a current, and then you can calculate power loss on these transmission lines, right? So you're just going to do this. The I of the lines times the V of the lines. Okay. And then you can use Ohm's law to make it a little bit easier. So the voltage on these transmission lines, remember they're very long, so you cannot ignore the voltage on that, okay? All right, and then you can get another expression. So this expression helps us to figure out a way to reduce the energy loss on the transmission lines. Okay, so let's take a look at this equation. Again, they're totally equivalent, right? I just rewrote this equation using Ohm's law, so I get I squared times R. And you may have seen this form of power equation in different resources, okay? But they're totally equivalent. You don't get like two different equations for power. There are two ways. So if I want to reduce, this is the power, right? And then how do I reduce the energy or loss on these power lines, these transmission lines? Well, if the power loss is very small, then if you can reduce the power loss, then the energy loss is going to be small, right? Because the energy is power times time. One way you can do is to reduce this resistance. How do you reduce the resistance of the transmission lines, right? This is how you calculate resistance. This resistivity times the length divided by the area, right? So if you want to make this R small, right? Because I want to make this power loss small. You make this guy very small. So you're going to find some good conductors, okay? That's something we can do. But you also need to make sure it's cheap, right? So if it's a very good conductor, but it's very expensive, so you still, gonna waste a lot of money. And then, but we're already using very good conductors in the transmission lines. So that's not much we can do about this guy. Another guy you can do is this, right? What about you reduce the length? But there's no way you can reduce the length, right? The power station is like 500 miles away from the city. You can't cut the distance in half, right? It's still going to be 500 miles. So there's nothing you can do about this guy, literally. Another thing you can do is that, okay, maybe I can make this guy larger, right? Make this area larger. Okay, make the cross-sectional area larger so that the resistance is going to be small. But that's going to be a stupid idea, right? If you make the cross-section area larger, you're going to make this transmission lines bigger and bigger. Again, it's going to cost more money, and it's going to become heavier and heavier, right? So it's going to become heavy, so it can even fall very easily, okay? So you're going to have like build some very strong towers to suspend these transmission lines. So that's going to be a stupid idea, okay? So there's not much you can do with the resistance, okay? If you want to reduce the power loss on transmission lines. Then that leaves us only with this guy. So if I can reduce the current on these power lines, so I can reduce the power loss, Okay, and that is a good idea because you see that there's a square here. So if I can reduce the current by a factor of 2, actually I reduce the energy by a factor of 4, which is good, right? If I reduce this by a factor of 10, I actually reduce the energy loss by a factor of 100, okay? So that's very good, that's very nice. So that's what we're doing in real life. So I want to reduce the current on these transmission lines when the power comes out from the power station. How do I do that? Remember, we just discussed transformers. If you use a transformer, it can change the voltage for you. But at the same time, the current is going to change, right? So we can make use of that. So we can place a transformer, okay? So if this is a power station, I'm not going to deliver the power directly. I'm going to have this guy connected to a transformer first, and then reduce the current, okay, and then use that right in the secondary to deliver the electricity to a city. So if you want to reduce the current you get from the secondary, so that's the current goes to the transmission lines, you would have to raise the voltage, right? Remember, the power is the same, right? If you want to get a lower current on the right hand side, right? You want to get this guy very low, you would have to raise the voltage, okay? So that is why all these transmission lines, they're at a very, very high voltage, because you have to, if you want to reduce the current on these transmission lines to save energy, okay? So that's what we do in real life. So when the electricity comes out from a power station, we're going to first raise the voltage, okay? Use the step-up transformer to raise the voltage to very high, so the current goes to very low, so the power loss, the energy loss on the transmission lines can be reduced, okay? And then when it comes to a community, okay, of course I'm not going to use that high voltage in my home, right? That's going to kill me, right? Then we place another transformer here, right, before it reaches anyone's home. So we reduce the voltage to a lower value, to a safe value, so that we can use that in our homes, right? So you will have a transformer here, and you're also going to see use a transformer here to lower it, right? So, and on this side, that's going to be your step down voltage, a step down transformer to lower the voltage to a safe voltage so people can use in their homes, right? Okay? So now we're going to see, again, it's always easy to understand the theory using a real problem with real numbers. So we're going to use this theory to calculate the energy loss on these transmission lines with and without raising the voltage, okay? And we're going to compare the energy loss in these two different cases. We're going to see how much it's going to save on the energy and money, okay? So that's what we're going to do now. So take a look at the question on slide 11. An electricity generating station needs to deliver energy at an average power of 2 megawatts to a city 23 miles away, right? Resistance of the wire is 70 ohms. You see that the resistance is already very low. The resistance of transmission lines 23 miles long. It's only 70 ohms, right? We have already reduced the resistance to very low. So there's not much you can do here. A common voltage for commercial power generator is 22 kilovolts. So that means the power comes from this power station is already 22 kilovolts. It's already a very high voltage, but it's not enough, okay? We're going to still raise that in order to save the energy and money. But right now, let's just use these 22 kilovolts, okay? So we are not changing the voltage at the moment. we're just gonna use the voltage from the power station and then deliver the electricity directly using that voltage, okay? And we're gonna see the energy lost on the transmission lines, okay? If we don't use any transformer to raise the voltage to the even higher value, okay? So we want to find, I want you to estimate the energy wasted in the wires during one day, okay? So this is a power station, okay? We don't use a transformer. We're just going to deliver that directly to the city using the voltage coming out from this guy, 22 kilovolts. And this guy wants to deliver 2 megawatts to the city, okay? So how do I calculate the energy lost, the energy wasted on these transmission lines? Well, we can do this, right? The energy loss is just going to be the power loss times time, right? And then the time, that's why the problem says, I want you to do that in 1 day. So the time you plug in is going to be 1 day. Of course, you're going to convert it to seconds, right? Everything is in SI units. So I have this. So then I just need to find the power loss on these transmission lines, then I multiply them. How do I find the power loss? We just derived that, right? So I can do I times V. But then I can use Ohm's law to rewrite this guy as I times R. So at the end I can do this. Okay, so this is going to be the current and everything on the transmission lines. Right? Now, how do I find these values? Okay, so we're going to use these two numbers to find the values. Okay, so then some people, they would just use like, okay, the voltage is just going to be 22 kilovolts. Okay, I'm going to plug that number. No, the 22 kilovolts is not the voltage on these transmission lines, right? Think about that. You want to deliver 22 kilovolts and 2 megawatts to the city. You actually want the transmission lines, they're going to take some voltage and power, but you want to reduce that to a minimum value. So you want this transmission lines to take only very small voltage from this number, right? If you say the voltage on the transmission lines is 22 kilovolts, that means the city gets nothing, right? The transmission lines already take away all the voltage, okay? So if I draw let's do this. If I draw an equivalent circuit for you, you know what I mean. So now, actually, there are two, you can consider the city and the transmission lines as two separate resistors in a circuit connected in series to a battery, okay? Then it's easy for you to see how the currents, voltages, and everything connected. So this is the lines. So I'm going to use this resistor to represent the lines, this resistor to represent the city. And this guy has 22 kilovolts. It wants to deliver 2 megawatts to the city. But the lines, it's here. The lines are going to take some voltage, right? Because from this diagram, I know that voltage from the lines plus the voltage from the city is going to be equal to 22 kilovolts, right? And the power of the lines, right, plus the power of the city, that's going to be equal to 2 megawatts. So your goal is that I want to deliver all this voltage, most of the power to the city. So I want these two numbers to be small, okay? So you don't know these two numbers. You want to find this power of these lines, okay? So how to do that, okay? So you don't know this voltage or this voltage. You just know the sum of them is going to be 22 kilovolts, okay? Now let's take a look at this equation. So if I rewrite this equation as I times R squared, so I only need to find the I. I don't need to find a V, right? Which I don't know. I don't know, okay? So I only have one variable to find because the resistance is already given, right? The resistance is 70 ohms. Okay, the problem says the resistance of the transmission lines is only 70 ohms. So all I need to do, just find the current on these transmission lines. I can find the power of the transmission lines. Then I'm going to multiply that by time to get the energy loss. Okay. Now, how do I find the current in this transmission line? Let's again use this equivalent, the simplified diagram, the circuit to help us, right? I only know this is going to be the total. So this is going to be the total voltage. This is going to be the total power delivered to this whole thing. Yeah, my goal, my purpose is to deliver everything to the city. But this guy, that's going to take something from the battery. Okay. But this is the, if I only need the current through this guy, okay, see that I only need the current on these transmission lines, but this is a series circuit. Actually, the current is the same everywhere, right? So if this is called I lines, I city, they are the same because they are connected in series, and that's going to be equal to the current total from the battery. Can you find the current, total current from the battery? Yes, you can. You can use these two numbers, right? Because I know that power for the battery doesn't know how many resistors are connected to it. The battery is just going to provide this voltage and then deliver this power. That's the problem says, right? And then this is always going to be true to the power, right? So if the power wants to deliver this voltage and this power, the battery wants to deliver this power at this voltage, you can find the current it's going to deliver to this whole circuit. Okay? And that current, it's going to be equal to the current through this resistor. It's going to be equal to this current through the second resistor because this is a circuit in series. That's how I find the current in these lines, right? I don't find it directly, but I use this series circuit. I just need to find the total current using these two numbers, okay? And then that's going to be equal to the current through the lines. Then I plug the current in, find the power loss, and the energy loss, okay? Now you can pause the video, finish the algebra, all right? Now let's see. The total current equals the current through the lines. It's going to be V total over, no, P total over V total. No, let me rewrite it. The power through the lines, according to the equivalent simplified circuit, is going to be equal to I total, which is going to be equal to P total over V total. Right? So what is this number? This number I found is 90.9 amps. Okay? So that's going to be 90.9 amps everywhere in this simplified circuit. Now I can go ahead and find the power loss. Right? So the power loss is just going to be I squared times R. R is here, I just found. So the power loss is going to be 5.785 times 10 to the 50 watts. Okay? Now let's pause here and take a look at this. It wants to deliver 2 megawatts, which is 2 times 10 to the 6th watts to the city. But this guy already takes almost 6 times 10 to the 5th, right? So this is how much? So 5 times this divided by, this is almost 30% of the P total. 30% of the power has been lost on this transmission line. The city only gets 70% of the power from the power station. Like, you really lose a lot of power on this transmission lines, right? All right. So then we can plug this power, this number into this equation. Remember, you can convert the time in seconds, right? So delta T is going to be 1 day, 24 hours times 3,600 seconds. That's the time you plug in, right? And then you should find 5.0 times 10 to the 10 joules. Okay, so that's the energy wasted on these transmission lines. 1 day, only 1 day. Okay. So, and you see that 1 day is going to lose so much energy, right? So joules and power of watts, if we calculate the power and then energy in electricity consumption, actually joules and watts, they're very small units. It's very easy to get a huge number, okay? So that's why electric companies, if you take the next slide, prefer to use kilowatts and kilowatt hours for power and energy, so that we don't get a huge number, right? We get a reasonable number. So kilowatt hour is a unit of energy, okay? If you heard about it, it's not a unit for power, it's a unit for energy. So kilowatt hour, this conversion, if you want to convert kilowatt hour to joules, this is how you convert. Well, all you need to do is this is actually a product of kilowatt and hour. So you just convert everything to SI units. 1,000 watts times 3,600 seconds, right? So that's how you feel. You don't even need people to give you this conversion, right? You know, if you know what kilowatt hours means, so you can convert that, okay? If you look at the electric bill you get every month, you can see the units in kilowatt hour. It's not going to be in joules, because if it's going to be in joules, it's going to be a huge number, okay? It's definitely going to freak you out, okay? So they usually bill us in kilowatt hours. So you're going to see the cost is like, you know, usually less than $1, 1 kilowatt hour, okay? And then it lists the kilowatt hours you use every month. So that's how they charge us, okay? Now the next part. So now I want you to estimate the cost of the energy wasted in the wires in 1 day. So I want you to calculate how much this costs, okay? So if the energy costs are about 11 cents per kilowatt hour, okay? So it's gonna be, if the energy cost is 11 cents per kilowatt hour, how much does this cost? How much does this cost? Well, you're just gonna convert this energy to kilowatt hours, right? Because you know the cost for 1 kilowatt hour. So you need to find out how many kilowatt hours is this. So you convert this to kilowatt hours and then multiply that by this number. You can get the cost of this energy wasted on these transmission lines. All right? So pause the video, do the algebra. So let's see. I'm gonna do it here. So you're gonna convert the energy loss to kilowatt hours, right? So you remember how to convert units? We have done that many times, right? You're just gonna put 3.6 times 10 to the 6 joules here, 1 kilowatt hours here, right? And then you can multiply, so the cost, it's gonna be 11 cents, which is gonna be $0.11 per kilowatt hour, then times this energy loss in kilowatt hours, right? So you can multiply these two numbers. So at the end, you will get this number. So that means that's the cost of this energy wasted on these transmission lines in 1 day, right? 1 day, it's gonna cost like more than $1,000, okay? And totally gone, down the drain, okay? It didn't get to deliver to the city. Totally wasted as heat on these transmission lines, $1,000 1 day, right? So no one likes that. The electric company doesn't like that, and we don't like that because we're gonna be paying this cost, right? They're not gonna absorb the cost themselves, okay? So now we're gonna see how can we make this better? How can we reduce the cost by using a transformer to raise the voltage, okay, from the power station, and then lower the current on these transmission lines, and then reduce the cost, the energy cost, loss on these transmission lines, okay? So that's what we're gonna do now. So we're gonna do that. We're gonna raise this guy, okay? So I'm not gonna deliver this guy, the electricity at 22 kilovolts. Even though it's already very high, it's not enough. I'm gonna even raise that to 330 kilovolts. So that's what I'm gonna do. I'm gonna place this guy in the transformer, okay? And then I'm gonna raise the voltage, okay, to a very high value. Then I'm gonna deliver that to the city, okay? Now let's see, how do I calculate the energy loss on these transmission lines if I raise it from 22 kilovolts to 330 kilovolts? So the steps are still the same, right? Now the only difference is this. I'm just gonna consider this circuit, right? I'm gonna draw this equivalent circuit for this part. Because now the transmission lines are connected directly to this transformer. So the transformer is like the source, right? Provides the voltage, current, power to these transmission lines and the city. So this is like the battery to these two resistors, right? So what is this battery? The battery, the only difference is this, right? So now the voltage you receive from the battery is not going to be 22 because I already raised it to 330 kilovolts. What about the power from the battery? That's still 2 megawatts, okay? Let's assume this transformer is still ideal, so it doesn't lose any energy. It only changes voltage and current, but the power on the secondary is still 2 megawatts. So it still delivers 2 megawatts to the lines and the city. Of course, it wants to deliver as much as possible to the city, but at the end, you will lose some power and energy on the line. So that's what we're going to calculate again. So the only difference, you see that, is this number. Now, we're still going to use this equivalent circuit. The only difference is that, oh, now it's connected to a battery with 330 kilovolts, the same total power provided from the battery, 2 megawatts. How do you calculate the power of this R1 and then the energy of this R1? Again, all I need is the current of this guy because the power of this guy is going to be I times R squared. R is still the same. What is this new I? The new I is still going to be equal to the I total. How do you find the I total? The P total is still going to be I total times V total, right? The step that's the same. The only change is this, right? The V total becomes a new value. So you're gonna find a lower I total, which is a lower current that goes to the transmission lines. That's our goal, right? We want to reduce the current on these transmission lines so that the energy loss will be reduced, okay? And once you have this I total, you're gonna still do this, find the power loss, and multiply this by the time find the energy loss, okay? All right, so you just repeat the same steps with this new voltage after the transformer, okay? Now you can pause the video, do the algebra. All right, so now let's see. If I do this, I'm gonna still get I total equals P total over V total. Right? And what is this number? Well, you divide these two numbers, the number I got is 6.06 amps. Okay? So that means now in this circuit, everyone gets this current. Everyone gets this current. Then what about this power, right? Well, that's going to be still the same equation, right? So now you can go ahead and plug all these numbers in. What is the power you get? Okay. So I found this is I lines times R line. Okay, you use this I total, you square that, multiply by R. The power I got is 2571 watts. Now again, let's pause here and compare this with the power from the battery, right? So 2071 divided by 2 mega. So that's about 0.1%, I believe. So this is almost like 1,000 times higher than this, right? 1,000 times larger than this. So you see that by raising the voltage, you still get some power lost on these transmission lines, but this is going to be 0.1, about 0.1% compared to the 30% we just did. Okay, we just saw in the previous part. Okay, so it's really a lot. Okay, now we can go ahead and find the energy loss. You just multiply this by the time. Time is the same, right? So the number I got is 2.22 times 10 to the 8 joules. So this still seems a large number, but remember, that's because joules and watts, they are very small units in electricity consumption, okay? Now I want you to finish the last part, so the last slide. Now let's see how much does this cost? How much does this cost? If the cost of the energy is still 11 cents per kilowatt hour. So you're just going to do the same thing, right? You just convert the energy to kilowatts and multiply this by the energy loss, okay? So let's see, what do we get? So now you're going to put this guy here. So that's going to give you the energy in kilowatts. And you multiply this by this, you will get 6.78 compared to the number we just erased. Okay, so by raising the voltage from 22 kilovolts to 330 kilovolts using a transformer, we were able to reduce the cost of this energy wasted on the transmission lines from more than $1,000 in a day to a few dollars in a day. So that's a lot of savings. So that is why, even though it seems like more work, it seems like more complicated to us, okay, but this saves a lot of energy, saves a lot of money. So that's why the electric company, they're still going to use the transformer to raise the voltage first and then bring it down when it reaches the city, okay? It sounds a lot more, some extra work, but it saves a lot energy and money. That's why, again, that's another reason we use AC in real life, because we can convert the voltage very easily using a transformer, okay? And which is going to help us reduce the energy loss on these transmission lines, all right? I'm going to stop here for this lecture.